Okay, we have an assignment that is due tonight. Hopefully you feel good about that. If not, I will be seeing you after class. I will be getting another assignment to you. I need to figure out whether I should make that due Monday, Tuesday, or Wednesday. Given the last couple times I've taught this course, it's not a bad thing, but we're moving at a slightly slower pace. So I have to just make absolutely sure that the material that is going to be due will have been covered, and you've had a chance to ask me some questions about it by the time I make the assignment due. The pressure, of course, is that the exam is next Friday, and it will cover most of the material on this next homework. So I want to make sure that you can get it in and get feedback on it, give the grader enough time to actually get it back to you so that you can study for the material that's on the exam. So those are the two variables that I'll be balancing when figuring out when that is due. Regardless, the typical process for this is that if you do submit it early, then I have the grader prioritize the assignments in the order that they are received. So if you're able to get it in early, that means you'd like feedback early. And so you're more likely to get that feedback earlier rather than the night before the exam. That'll give you a ton of time to study. All right, we were in the process of figuring out how to do DFA reductions. We had started by saying that we should remove any inaccessible states. We do that with finding all simple paths from the start state of the graph and figure out, okay, what states can we not reach by iterating all of those simple paths. From there, we are going to make a diagonal table or a half table, however we want to name that in this class. I introduced that idea at the very end of the last class, but now we're going to actually dive in and see what is the process of determining whether pairs of states are distinguishable or indistinguishable. So we start with all pairs of states. The initial pass through this half table is going to be looking at the finality of those pairs of states. If one of those states is final and one of those states is non-final, we will mark that pair as distinguishable. Then we're going to enter a loop. The termination condition of that loop is that we make no changes in the table. As soon as we make a single change, mark a single pair of states as distinguishable, we must go through this loop again. Once we make no changes to the table, then we can terminate. You're going to look at every pair of states where we have a question mark in that table. So we're going to have three symbols that we're going to use in this table. There is the D marking distinguishable. There's the question mark. That is, we haven't yet shown whether this is distinguishable. And then at the very end, we'll fill in all remaining blanks with an I, indistinguishable, saying that if we could have shown they were distinguishable, we would have done so by now. So for all pairs of states that are currently question marks, we're going to then look at the transitions for every input character from each of those states. So we're going to pretend that one process is in one state, one process is in the other, and say, where do we end up when we take an A transition? What is that pair of states? You're going to look up the destination pair of states in the table and see if we've marked that as distinguishable. If we have, then we will backtrack and mark the initial pair of states as distinguishable. Continue this process for that pair of states for every alphabet character. And if we can't conclude anything, we will leave it as a question mark. But if we find that the pairs of states that are the destinations are ever distinguishable, we backtrack and make that distinguishable. I'll have an example of this so that it's not just a theoretical idea. We'll actually go through this process. But yeah, if the new pair of states is distinguishable, mark the pair that we started with as distinguishable. And don't worry so much about the equivalence classes for the moment. We can get all the information that we need from the table. If we go through this process, by the time this loop terminates, we go through every question mark and don't change a single one of them into distinguishable. That means that every remaining pair is indistinguishable. We would have made some change or another to some state at each position if they were distinguishable. We can show mathematically that everything that remains is indistinguishable. Any questions as a theory before we go into and do an example? Let's do it. Here's the DFA. Very first thing you might want to think when looking at this DFA is intuitively, is this a minimal DFA? Are there any obvious states that can be removed or combined? It's kind of a test of your intuition. I may have given this to you because there are no states that can be combined. I may have given this to you because there are some states that can be combined. I can make this table ever so slightly smaller if I don't put Q0 on either a row or a column, because there is, if you do that, there is some row or column that gets X's all the way through it. So there's just no reason. We don't need to compare Q1 to Q1. We don't need to compare Q2 to Q1 or Q2, Q3 to Q1, Q2, or Q3. And this Q4, I guess, we didn't really need this here either. So we care about this diagonal table, comparing Q0 to Q1, Q1 to Q2, Q2 to Q3. So it's 0 to 1, 2, 3, and 4, 1 to 2, 3, and 4, 2 to 3 and 4, and 3 just to 4. I'll move this over so that it actually looks like, and we can actually draw this as a row table. All right, this is everything we're actually going to need to fill in. Everything in the diagonal, this diagonal table. So first step, we're going to mark pairs of states that have different finality as distinguishable. So looking at Q0, what are the set of states that have a different finality from Q0? Q2 and Q4. So we're going to, in the row of Q0, mark Q2 and Q4 as distinguishable. Immediately, those pairs of states have different finality. Q1, what are the set of states, Q2, Q3, and Q4, that have different finality from Q1? Same states, Q2 and Q4, those are distinguishable. From Q2, just looking at Q3 and Q4. Q3, distinguishable, since Q2 is final. Q3 is non-final, that gets the distinguished label as well. And are Q3 and Q4 different? Yes. So what's left are question marks. We don't know whether these states can be combined at the moment. So we're going to loop and look at every pair of states that has a question mark. And we're going to ask about every character in the alphabet. So let's start with our first question mark, Q0, Q1. At this point, every pair of states that you look at should have the same finality. But imagine being in Q0 and in Q1. Where do we end up when we consume a zero from there?
Q1 or Q2.
We end up doing that, following the zero transition from each one. We end up in Q1, Q2. We're going to look back at the table at Q1, Q2. Is that distinguishable? Yes. So we are going to backtrack and mark where we came from as distinguishable. That is the evidence that Q0 and Q1 are doing different things. That tells us the string that we would use in order to, if we somehow got to that pair of states, this is the string that ends up in eventual different finality, where one of those strings from that state is accepted, one of them is rejected. About Q0 and Q3. Where do we end up on a zero? We end up in Q2 and on a zero. If we're looking at Q0 and Q3,
Q1.
Q1 and Q2. Q0 goes to Q1, Q3 goes to Q2. So looking at 1, 2, that's exactly where we ended up before. That's distinguishable. So we'll backtrack and mark this as distinguishable.
Can you go over that again, please?
Yeah, so we start in Q0 and Q3 on a zero. This goes here, this goes here.
Oh, I see.
So we ended up at Q1, Q2. Q1, Q2 in our table was distinguishable. So we will backtrack to where we began, Q0, Q3, and mark that pair as distinguishable in the table. Question?
It still works with like 1, right?
Yeah. Yeah. I'm just starting with 0 because it's the first character in the alphabet. But in order to keep this as a question mark, we would have had to go through both 0 and 1. And they would both have to be inconclusive. Let's look at Q1 and Q3. On a 0, we end up in Q2 and Q2. And on a 1, we end up in Q4 and Q4. And by definition, a state is not distinguishable from itself. So we currently can make no conclusion. Looking at Q2 and Q4. On a 0, we end up in Q1, Q4. This goes here, this stays here. Q1, Q4 in the table is distinguishable, so we will backtrack and mark Q2, Q4 as distinguishable. Since we made at least one change to this table, we need to loop back around and look at the question mark again. Because it's possible that one of these changes that we marked as distinguishable after we looked at this pair now means that this becomes one of those destination pairs. If that becomes one of those destination pairs, it's something we have to recheck. So looking at Q1 and Q3 again, on a 0, they still end up in Q2 and Q2. And on a 1, it's still Q4 and Q4. So because of this no change, we've looked at every single question mark in this table. So we can terminate the loop. Every question mark can now be replaced with an indistinguishable marker, which means that those pair of states can be combined. So let's talk about how we go through that combine process. So we're marking Q1 and Q3, saying that there's no reason to have both of these. We just need one of them. And in fact, it doesn't matter which one we keep. We just need to keep one and delete the other. So which one do we want to keep? Do we want to keep Q1 or Q3? The fate of the world is in your hands. Keep Q1, get rid of Q3. All right, so imagine that this state doesn't exist. Every outgoing edge to this Doesn't matter. So we're going to get rid of this edge. We're going to get rid of this edge. But every incoming edge needs to be redirected to the equivalent edge. So everything coming into Q3 from anywhere now needs to go into Q1. So the edge from Q0 to Q3 that was a 1 now needs to be rerouted over to Q1 before we can get rid of it. Take a second and look at this. I made some changes. Is there any string that is now accepted that used to be rejected, or rejected that used to be accepted? Or does this new diagram that has one fewer state accept exactly the same language?
It's the same.
Yeah, this should be the same if we've done this correctly. This is a way to check your work on similar kinds of problems to this. Just take a second, take a step back, intuitively look at your result and the original, and say, is this logically equivalent?
A question, backtracking just a little.
Yeah.
How did you note that like X out Q1, Q1, Q2, Q2, and Q2, and Q1?
Because it's supposed to be pairs of states, and if it's the same state, there's no way that a state can be distinguishable from itself. But also the process of combining a state with itself is the easiest thing you've ever done. So it's just a question that we don't have to ask.
Well, you could do the same thing, except you could flip it and it'd be the same. If you crossed out all the ones on top and then did the ones on the.
Yeah, it's commutative.
Yeah.
Distinguishability, it doesn't matter which comes first and which comes second in that, which is why you can take out either half of this table as long as you're filling out every combination where order doesn't matter. Great question. Other questions? Other thoughts on this process? There's a bit of complexity here, so I would kind of expect there to be a little bit of back and forth from this. Is there any lingering confusion or how much sense does this process make when laid out? Maybe show some thumbs. How are you feeling about this?
Sure.
Yeah, that's good. I do see a few below mid, so I think it would be worth going through another example, but I need to figure out if I have another example. I do not remember if I have another example. All right, so we go through the process that we've already gone through, but just in slide form. Don't worry about the concept of equivalence classes here. This is really just talking about the pairs of states. The equivalence classes would be factored out into the eventual pairs of states. I've just cut this from my explanation because I feel like it overcomplicates it in a way that is unnecessary and doesn't lead to a better result. But it's the way the book explains it. I think the way I explain it is simpler and does exactly the same thing. Then we talk about constructing the minimal DFA. What do we need to do in order to do that? And we find that we can combine states 1 and 3. And it is unfortunately the only example that I have of this process. So I would like to find another one of those. The question is, what I should probably do is pull one from the book, and I don't have the book out and accessible, and I don't want to take 10 minutes looking it up. Does anyone have a copy of the book with them? Yeah, so maybe if I start explaining something that is next, someone can look up a practice problem that I can use from that section of the book. Otherwise, we could start next class with it. And I can prepare it between today and tomorrow. That does not waste people's time. Yeah, I think that's probably the best course of action. I'll look up a practice problem between today and tomorrow. We'll start tomorrow's class with another example of DFA reduction. It's not on the current homework, so I don't feel super pressed for time, but it will be on the next homework. So I should get to it before you're there in the homework. Okay, next order of business is to talk about regular expressions. So we've been talking about this concept of regular languages, but there are other ways to describe regular languages other than just the tools that we have seen so far, DFAs and NFAs. There are a couple of other ways to express that class of language. So we're going to look at both of those next. The first one is regular expressions. Who's heard of regular expressions before or have used them in some capacity? Some people, but not some other people. So this will be useful. So one way is via regular expressions, and they look very much like math expressions, but they're made up of some baseline components. And in fact, regular expressions are used a lot in text search. So this has use outside of just theoretical language construction. It's very useful in day-to-day life, even in searching documents, and it even shows up in some games and the ability to script or mod some games. It's very, very useful. All right, so like an expression, they're made up of symbols. Those possible symbols are strings and symbols from the alphabet and combinations of characters in the alphabet. You can have parentheses. There are operators, just like in math. The plus operator in a regular expression denotes set union. The dot denotes string concatenation. A superscript star is still star closure, meaning just 0 or more repetitions of what comes before it. And that's it. Motivationally, they can be used as a complex search function in text editors or browsers that support it. I highly recommend the first thing you do after this class is go install a regular expression extension to whatever browser you use to allow yourself to use regular expressions in your Control F binds, in anything else. You can do things like search for all phone numbers. Doesn't matter what the digits are, all phone numbers. You could find all 2-digit numbers. You could find all sequences of 3 lowercase letters followed by 2 uppercase letters followed by a dash. Something like that, denoting structure in your search, not just the exact string match. They're becoming more popular in any item-driven games. So I play Path of Exile every once in a while, and you can throw regular expressions in your stash search, and it will highlight items that match exact combinations of mods, or socket layouts, or link layouts, or items that have modifiers within particular values. Things that might otherwise be very difficult to do. It will immediately find those items for you. So very useful in random contexts that have nothing to do with computer science, where if you know what it is, then you look like a genius. So Path of Exile is my go-to example of that, just because it's what I have experience with. But there are, I'm sure, are others. Let's give you an example of a regular expression. So here's our alphabet. A regular expression could denote a language saying A plus B dot C, all of that star. The way you can read this might be to kind of start from the outside and work its way inside in terms of English. So it's the star closure of A union BC. This makes an interesting language. If we see this as the left-hand side, and this is the right-hand side, we can start making combinations of the left-hand side and right-hand side. So since this is the star closure, we can take 0 elements. If we take 0 elements, we end up with the empty set, or I guess the empty string. So lambda is an element of this language, string in this language. We could take everything where we have one instance of a left-hand side or right-hand side. So let's take the left-hand side, that's a string in this language. We'll take the right-hand side, that's a string in this language. Now we can take all combinations of 2, left, 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 right, right, left, and right, right. So left, left is AA. Left, right is ABC. Right, left is BCA. And right, right is BCBC. All of those are in the language. Then we can start looking at all combinations of 3. Left, 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 right, left, right, left, etc. So this would go on where we have all instances of 0, all instances of 1, and all instances of 2. 0, 1, and 2. And as you see, as this is combinatorics, just like every other time, since there are 2 elements, left-hand side and right-hand side, there are 2 to the 0 elements of this, there are 2 to the 1 elements of this, there are 2 squared elements of this, and that process would continue for 3s, 4s, 5s, 6s, etc. So that's kind of the structure of how I would create an infinite set containing strings in this language. So that's how I look at a regular expression, and then how to convert from the concept of a regular expression down into what is in this language. Questions on anything from here? Actually, go through the work before I reveal it. There's a similarity to recursion here. I kind of have a recursive definition of, you could make a tree that starts out as the empty string. As a left child, you're going to append the left-hand side. As the right child, you're going to append the right-hand side. So you would start with a root node that is lambda. From here, we append the left-hand side, A. From here, we append the right-hand side, BC. From here, we append the left-hand side. From here, we append the right-hand side. We could iterate it like a tree. And now we could search this in depth first order, in breadth first order, in any other way that makes sense. There's similarity to constructing mathematical expressions as well, where if I asked you about evaluating a mathematical expression, You start with any inside function and then slowly work your way out. We determined the left-hand side and the right-hand side. What was the right-hand side from applying the concatenation from the left-hand side? The value of this says left-hand side, evaluate this to be the right-hand side, and then star closure is that repetition that creates that recursive relationship. So tools we have for construction, primitive regular expressions are just the empty set. This is the regular expression that has no elements. Lambda is the regular expression that just expresses the empty string. Then we have every character in our alphabet. Each of these are regular expressions that can't be broken down further. They're the primitive variables of regular expressions. We can use those primitive regular expressions to construct what is similar to an object regular expression that can be broken down into its primitives. So we can now union together two regular expressions, concatenate together two regular expressions, star closure a regular expression, and throw a regular expression in parentheses. And now through repeated use of this, where each component is either one of these or a complex version that breaks down into those, we can now construct more and more complicated regular expressions. Very much like math expressions. So we call something a regular expression only if it can be derived from combinations that break down into those primitives. How are we doing? Any questions?
What does the R1 in parentheses mean?
It just means that we can surround a regular expression with parentheses that says we can break the typical order of operations that we'll talk about. So yeah, regular expressions have an order of operations because just like in math, and I think I talked about this on the next slide, but we need some way to represent a regular expression without ambiguity. So there's a typical order of operations, and parentheses allow us to break that typical order of operations. All right. We have a language denoted by a regular expression defined by rules. Regular expression denoting the empty set. Regular expression denoting the set that is just the empty string. For every character in the alphabet, we have a regular expression denoting just the set that contains that character. Then if we have two regular expressions, we have ways of looking at them in terms of sets. So we're just now converting the idea of regular expressions down into set notation. So if we have a language defined by the union of two regular expressions, it's the equivalent of taking those two languages and unioning those two languages. All strings that would be accepted in one language, the other language, or both. That's what we mean when we say two regular expressions, and with plus, we're doing the equivalent of unioning them together. Same thing with concatenation. We have two regular expressions that are concatenated together. The language of that is the equivalent of saying, let's take the concatenation of the languages represented by those regular expressions. And as you might know from math, if we have two sets of parentheses without anything in between, we can get rid of the outermost set of parentheses. It doesn't do anything extra for us. And we can also strip out outermost parentheses, including one that is outside of us or inside of a star closure. So the star closure of the language of R1 star is the same thing as an extra set of parentheses around that, and then repeat that. And the entire reason we talk about these last four rules is it allows us, when we have more complicated regular expressions, we can simplify them. So these are the rules of simplification. And the first three rules are base cases for that recursion. In general, I won't ask you too many questions about this. I think there's a homework question or two about simplifying, but outside of that, I don't find this to be the most useful topic that we cover in general. But being able to identify regular expressions for languages and represent a language with a regular expression, we'll get to that, and it's much more important. So here's an example. Can we break the language defined by this regular expression down into set notation? So what are the strings that are in this language? Find some way of doing that. We can either attempt to simplify, if it is possible for us to simplify, or just look at this regular expression and try to break it down into some components that allow you to put together a structure for the strings that are in this language. So you could, equivalently, when we have the concatenation, you can take that and break that down into its associated languages. So we have the language of the left-hand side concatenated with the language of the right-hand side, which is kind of what I did in the example that I had at the very beginning of this. I said there's a left-hand side and a right-hand side, and it was broken down by concatenation. This is how you would show that we can break that down by concatenation. When we have the set union, we can now break that down into its associated languages. These are now the base cases of that recursion. The language of A is not an infinite language. It's a language that accepts one string, A. So from here, we can see that we have a left-hand side and a right-hand side that's concatenated together, just like before, or I guess in math, if you have AB, it means A times B. You don't need the dot in between them to signify multiplication. Concatenation in math is multiplication. Similarly, with regular expressions, you don't need the dot to represent concatenation. If you just have two things next to each other, by default, it means concatenation. And on the right-hand side, we have to pick one or the other, an A or a B. How could we represent this set in some way that is useful? How could we start writing out the strings that are in this language? Is there a useful ordering that would help us to see that structure? Maybe I can clarify that, because there are a couple ways to think about this. One of which creates the way that I see it, one of it creates a two-dimensional problem, and one of it creates a one-dimensional problem. And in general, a one-dimensional problem is better than a two-dimensional problem. We want some ordering where we eventually get to everything without having to say, this process goes forever, but when it finishes, go do the next thing. You can imagine something like count to infinity. And when you get there, take a step forward. You're never going to get there, so it's a process that doesn't have a conclusion. You could do something, though, that says something like, count to 10, take a step forward. Count to 10, take a step back. Go from 10 to 20, take a step forward. And now you have a process that will actually get to everything, even though it's still infinite. So this language is infinite, but if we start with kind of the left-hand side, the language of A star, we have 0 A's, 1 A, 2 A's, 3 A's. So if we pick, just do this left-hand side paired with this, we're never going to get to this right-hand side. And append the B to the end of this. So the order in here would be 0 A's plus A, that's an A. 1 A plus A, that's 2 A's. 2 A's plus an A, that's 3 A's. This process goes on forever, and we never include anything that is the B's in this process. We would have to say this goes forever, and when we finish it, now have 0 A's plus a B. And you end up with a set notation that ends up with 2 dot dot dots in it. And that's generally worse than if we can find a way to combine this. So let's go with 0 A's plus the A, 0 A's plus the B, 1 A plus the A, 1 A plus the B, 1 A plus 2 A's plus the A, 2 A's plus the B. And now we have a process that has a single dot 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 on the end of it. So both of these, if allowed to go forever, represent the same idea, but to me, one is simpler than the other. It incorporates the structure into the process, rather than breaking it apart in a dimension that doesn't make sense. So just ways to think about infinite languages. Yeah, once you've broken this down into its base case components, then you can start working with that and then break it down into a way that makes sense. And here I have signified the way that has 2 ellipses in it. And we'll talk about more of this in detail later on when we talk about the theory of computation. Questions before moving on to precedence? Order of operations? All right, just like in math, we need to avoid the ambiguity, so we're going to define an order of operations. Without precedence, A dot B plus C, do we concatenate first or do we union first? We create a different language depending on the order of operations. Do people see how that's a different language if we prioritize one over the other versus the other over the one? A dot B plus C says that we should concatenate first. So we get AB union C. If we union first, then we get B union C. And then we append the A. So taking B or C, then that, unioning here says we get ABC. Here we get AB and AC. So different languages with different sets of strings, just based on the order of operations. So we need a default. We use these symbols because it's exactly the same order of operations if you assumed that the symbols were their mathematical counterpart. So star closure looks like an exponent because it happens first. Concatenation looks like multiplication because that's a lower precedent than exponentiation. We use the plus for union because addition is a lower precedence than multiplication. Why be confusing when we don't have to be? And just like in math, we can omit the dot for concatenation, and parentheses exist to override this default order of operations. It's not itself an order of operation, because there's no meaning to the parentheses except do this first. It's not its own operator, it's an overriding to existing operator precedence. Questions on precedence? This is hopefully not terribly surprising. And I honestly think there's no easier way to do this. It notationally is consistent with what you've seen before. All right, with the last few minutes of class, let's dive into a practice problem. Let's find the elements of this set. Let's see if we can find a way of ordering the strings that are in this language in some way that makes sense. We have A or B, star closure, A or BB. And try to find a way to order this where your eventual set notation only has one ellipse for continuing the pattern. We'll come back and get an answer to this tomorrow. We are out of time. I will also find an additional problem for DFA reduction. I have office hours starting now, and I hope we're going to be very busy.